Hey everyone, and welcome back to the mathematics course. Now I'd like to start lecture 8, derivatives. So derivatives is one of the most important topics that we're going to talk about. And let me start by an introduction to this topic. So let's assume that you want to drive from Jerusalem, starting by Jerusalem to Tel Aviv. Okay? And here the x-axis represents the time, and the y-axis represents the distance. And now suppose that you take your car and you start driving, and the function here represents the speed. Okay? Now, let's say that it takes 1 hour to get from Jerusalem to Tel Aviv. Now, if I ask you how fast were you driving on the road from Jerusalem to Tel Aviv, and let's assume that the distance from Jerusalem to Tel Aviv is, let's say, 100 kilometers. Okay, so you'll say that the speed, maybe you'll say that the speed, it's how far is Jerusalem from Tel Aviv, so the distance that I drove, over the time that passed, so 1 minus 0, so 100 kilometers per hour. Okay, now if you said that the speed is 100 kilometers per hour, that means that all the way you drove 100 kilometers per hour. But as you can see here, the function of the speed is not linear. If it's not linear, that means that the speed changed all the way. And if you don't believe me, what you could do is to say, let's look at half of the time, and let's see how much we passed. Okay, what distance exactly we passed. So we passed this distance. Now the other part, okay, the other half, we passed more distance. Okay, and that means that the speed is not constant. Okay, is changing over time. Okay, so that means that at the beginning the speed was a bit low, and then I drove faster. Okay, because I passed more distance. Okay, so what 100 exactly means here? 100 kilometers per hour. That's the average speed. Okay, average speed. Okay, and how exactly it looks on the graph? That's the chord that connects both endpoints here. Okay. Now what I'm going to do is to ask the question: what is the exact speed that I drove on this specific time? Okay, so the exact speed that I drove on the specific time, okay, on each of those moments here. Okay, so in order to explain how we are going to do that, let me change a bit the graph. So instead of speed, I'm going to call the function f. Here, instead of 0.5, let's denote it as TO. And 1, let's say that that's TO, that's the time, TO, when I added some time h. So here, the difference here is h. Okay, so h needs to be, of course, positive. Okay, and now let's say that we want to compute the average speed. Okay, so here we said that that's the average speed. Now, according to those notation, how exactly we're going to compute the average speed? So the average speed, that's the difference of the distance that we passed. Okay, so here that's not 100 anymore. Okay, that's going to be f of TO plus h, and here it's f TO. Now, in order to compute the average speed, I'm going to compute the difference of the distance. Okay, so that's going to be FTO plus h minus FTO over the time that passed, okay, from this point to this one. So TO plus h minus TO. And that's going to give me what? The average speed from TO 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 plus h. Okay, let me maybe erase the yellow code here. It's going to be much easier to understand what I'm doing. So again, I want to compute the average speed from TO 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 plus h, okay, TO 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 plus h, when I know that the distance at the point TO is FTO, and the distance at TO plus h is FTO plus h. So how exactly am I going to do that? I'm going to take the difference of the distance that I passed over the distance of the time that passed, and that's what's going to give me the average speed. So let's do the algebra here. We'll get that that's FTO plus h minus FTO over h. So again, that's the average speed. Now, the question is, suppose that I want to know the exact speed at TO, not the average speed, okay? What is the speed at TO exactly? So what I can do here, so is to do what? If you want from TO plus h to get to TO, okay? So you need h to be approximately 0. You need h to approach 0, because if h approaches 0, TO plus h is going to approach TO. And that means that if you want the exact speed, you'll need to do what? To take the limit when h approaches 0 of the average speed. Now, in general, we don't think about it as the exact speed, okay? We're not going to say the exact speed. Many times it's what we call the instantaneous rate. Okay, so instead of writing the exact speed, we're going to say that that's the instantaneous rate. And that's how we define the derivatives of f also. So the derivative of f, that is denoted as f tag x, okay? The first derivative of f, it's again denoted as f tag x. That's the limit when h approaches 0 of FTO plus h minus FTO over h. That's the definition. So that's the derivative of f at the point TO. Let me just fix it. TO. Okay. another way, okay, another way to compute the derivative. So let me write here the derivative of f at the point TO. So that's the definition. Now there's another way. There's another formula, and that comes from this one. Okay, so if you define a t to be TO plus h, then from here you'll get that the derivative of f at the point TO, that's the limit of f. Now TO plus h is denoted as t, so ft minus ftO, that stays the same, over h. Now if t equals to TO plus h, that means that h equals to t minus TO. So t minus TO. Now when h goes to 0, t approaches TO. So t approaches TO. And that's another way to define the derivative of f at the point TO. Okay, so till now it was an introduction to how to get the definition of the derivative of f at a specific point. Now we'll see the interpretation, the geometrical interpretation of the derivative, and then we'll start talking about how, in general, we compute derivatives of different functions. So let's continue on the next slide. Now, geometrically, the derivative of a function at a given point, let's say TO, is the slope of the tangent to at the point. Okay, now let me try to explain what it means. Now, we said that we are going to take h to 0, so h approaches 0. Now, we started with the code that starts at TO and ends at TO plus h. Now, think about it. If we take h to 0, now what happens here each time? So h becomes smaller and smaller. Now, if it becomes smaller and smaller, so that means that you'll see that the code is changing every time until it gets to the tangent at the point TO. And if you remember, we are computing the instantaneous rate. So now we are computing the difference of f over the difference of x. And that's exactly the slope, okay? So basically, again, when we take h to 0, okay, when h approaches 0, you'll see that the tangent is changing until it gets to be the tangent at the point TO, okay? And then you'll see that that's exactly the slope of this tangent. Why is the slope of this tangent? Because if you remember how exactly we computed the derivative, we took the difference of the distance over the difference of the time that passed. And that's exactly the slope of the tangent that passes through the TO point, okay? So now we're going to practice and see exactly how we compute derivatives of different functions. Okay, so now suppose that you have a function f of x equals to x squared. And we want to, okay, so that's the first example. We want to compute the derivative of f at the point x equals to a. Okay, so how exactly we're going to do that? We can use the definition, one of the definition. I'll use the second one, okay? So according to the definition, f tag a, the derivative at the point a of f, equals to the limit when x approaches a. Now you understand why we needed to talk about limits of f of x minus f of a over x minus a. Okay? Now, f of a, that's exactly, okay? Maybe before I'll say that f of x is defined as x squared. F of a, that's a squared over x minus a. Now, those are classics because you know exactly what to do here. You'll need to factorize the numerator, x minus a, x plus a, over x minus a. Here they cancel, and you'll get that. That equals to the limit when x approaches a of x plus a. And that's exactly a plus a, meaning 2a. So from here you understand that the derivative of f at the point a, that's 2a. Now if you want to understand what it means geometrically, x squared looks like that. And that means that at any point, for example here, suppose that it's 2 here, okay? If it's 2 here, then the tangent at the point 2 has a slope that equals to, so the slope of the tangent is 2 times a. In this case, a is 2, so 2 times 2, meaning 4. Okay? So now from here, we get the general formula. So in general, if you want to compute if f of x equals to x squared, and you want to compute the derivative of x, so what you need to do is to compute 2 times x. Okay? How exactly I got this conclusion from here? So here the function was x squared. And in the end, I want to compute the derivative of f at a, and I got that it's 2 times a. So 2 times a, so that means that the derivative at the point, in this case, I denoted that as x, it could be a, okay? It can be also any letter that you choose, okay? So it doesn't matter if it's x or t or anything else, okay? But in general, if you take the derivative of f at a specific point, you'll get that it's 2x, in case that, of course, f of x is defined as x squared. And in general, even more general than the previous one, if you have a function, let's denote this as g of x. We won't prove that, okay? But you'll need to believe that that's, okay? That's true. If you have a function that is defined as x to the power of alpha, that's the Greek letter alpha, yes? Alpha. Then the derivative of g is alpha times x to the power of alpha minus 1. Okay? And you can see that it's exactly what we got here. Okay? What is the derivative of f? It's 2. Okay? So think about 2 as alpha. It's 2 times x to the power of 2 minus 1. That's exactly 1. So 2 times x to the power of 1, that's exactly 2x. Now I want to mention a very important remark regarding this formula. This formula true in the case when alpha is positive. So if alpha is positive, so it works for any x. But if alpha is less than 0, it cannot be applied in case x equals to 0. The reason is that in case that alpha is less than 0, so x to the power of alpha, that's 1 over x to the power of minus alpha. Okay? And in this case, x cannot be 0 because x is in the denominator. Okay? So in this case, you can't really apply this formula. You can use this formula. Okay? So it cannot be used. Maybe I'm right. It cannot be used. Okay. Great. Now let's solve different question by using this general formula. Okay, so we said that the general formula said that if f of x equals to x to the power of alpha, then the derivative is alpha times x to the power of alpha minus 1. And again, please remember that in case that alpha is negative, x cannot be 0. Okay. Great. Now suppose that now you are asked to compute the derivative of the function x to the power of 5. So according to the formula, f of x, that's 5 times x to the power of 5 minus 1, meaning 5x to the power of 4. Another example. Suppose that f of x equals to x to the power of 2.5. And you are asked to compute the derivative of f. So it's 2.5 times x to the power of 2.5 minus 1, meaning 2.5 x to the power of 1.5. Next, suppose that you are asked to compute the derivative of x to the power of minus 2. So the derivative is what? It's minus 2 times x to the power of minus 2 minus 1, meaning minus 3. Another way to write it is minus 2 over x to the power of 3. Another example, suppose that you need to compute the derivative of the square root of x. So you can write f of x as x to the power of 1 half. That's exactly the same. Okay, so now you can compute the derivative. How exactly? By saying that f of x, that's 1 half times x to the power of 1 half minus 1. 1 half minus 1, that's minus 1 half. So what do we get here? It's 1 over 2 x to the power of 1 half. But x to the power of 1 half, that's exactly the square root of x. So it's 2 times the square root of x. So please remember this formula because we're going to use it many times. Okay. What about this example? F of x equals to 1 over x. So in this case, what we can do is to write f of x as x to the power of minus 1 and then use the formula. So f of x, that's minus 1 times x to the power of minus 1 meaning minus 2, meaning minus 1 over x squared. Okay. What happens here in case that the function is constant? So, for example, f of x equals to 5. What is the derivative in this case? So, first of all, I hope that even if you don't know the general formula here, I hope that you can understand that the derivative needs to be 0. Why it needs to be 0? Because if you think about the geometrical interpretation of what the derivative means, you need to understand that the derivative must be 0. Because f of x equals to 5, that's how the function looks like. Now, any tangent that passes through 2 points here, the slope is 0. Okay? The slope of a constant function is always 0. And therefore, you expect that the derivative needs to be 0. Now, if you don't believe me, you can also use the definition of the derivative. So let's compute the derivative by using the definition. So f of x minus f of, let's say, a over x minus a when x approaches a. Now, let's say that we want to compute the derivative at the point, yes, 1. And you know that the function always returns 5. So from here, if the function always returns 5, so f of x equals to 5. What about f of a? Well, f of a? F of a now, instead of a, we need to write 1 because we want to compute the derivative at the point 1. F of 1 also is 5 because f always returns 5 over x minus 1. So here we have 5 minus 5. Of course, that needs to be 0. Okay, so the derivative of a constant, a function that is constant, okay, is always 0. Now, another way to show that is to say that the function here can be written as 5 times x to the power of 0. Because x to the power of 0, that's exactly 1. Now, what is the derivative here of x? So I'll mention it in a few minutes, but in the end, 5 here, when it multiplies the function, it doesn't affect the derivatives, and I'll mention it in a few minutes. Anyway, you get 5 times, what is the derivative of x to the power of 0? That's 0 times x to the power of 0 minus 1 minus 1, and that's of course 0. Okay, so that's another way to explain why the derivative of a function that is constant needs to be 0. Okay, now let's continue. Now I want to talk about the derivative of the function e to the power of x. Okay, now here it's easy, okay, because here, without even, I won't prove that, okay, but you need to believe me that the derivative here of the function e to the power of x, that's exactly the same, e to the power of x, so it doesn't change here. So that's a formula that we can use in any case, okay? So here I skip the explanation, okay, because we never talked about the how to compute the derivative of an exponential function in general, and there we need to know what a logarithm is, okay, so we are going to skip it for now, okay. Now let's talk about different rules of derivatives. When I say rules of derivatives, I mean arithmetic rules. I'm not doing by arithmetic rules. So, for example, so the first rule says that if you have a function f of x and you add it and you add to it another function, you want to compute the derivative of the sum of two functions over the difference of those two, okay? Then what you need to do is to compute the derivative of the first one and add or subtract, depends on what you want to do, the derivative of two. Okay, so let's see how we use that in general. So how we use that in general. For example, if I ask you to compute the derivative of x cubed plus the square root of x, that's exactly computing the derivative of x cubed plus the square root of x. Okay, so let's see how we use that in general. For example, if I ask you to compute the derivative of x cubed plus the square root of x, that's exactly computing the derivative of x cubed plus the square root of x. plus computing the derivative of the square root of x. And that's 3 times x to the power of 2 plus, okay, we already computed the derivative of the square root of x. That's 1 over 2 times the square root of x. Next, another example. Suppose that you need to compute the derivative of x plus the square root of x over the third root of x. Now, what you can do here is to split the fraction here into, before even computing the derivative, into x over the third root of x plus the square root of x over the third root of x. And then, again, before computing the derivative, let's arrange it a bit. So what is the third root of x? That can be written as x to the power of 1/3. What do we have here? We have x over x to the power of 1/3 plus x to the power of the square root of x to the power of 1/2 over x to the power of 1/3. Okay? And now we can use, again, the exponential rules that says that x to the power of m over x to the power of n, that's x to the power of m minus n. So let's use that. So it's x to the power of 1 minus 1/3 plus x to the power of 1/2 minus 1/3. And again, we want to compute the derivative of that. So it's x to the power of 2/3 plus x to the power of 1 over 6. And then we want to compute the derivative of that. So now it's easier to compute the derivative because now we can use the first rule. So it's 2/3 times x to the power of 2/3 minus 1 plus 1 over 6 times x to the power of 1 over 6 minus 1. And that's exactly 2/3 times x to the power of minus 1/3 plus 1 over 6 times x to the power of minus 5 over 6. Another way to write this is that it's 2 over 3. And then here we can write the third root of x. Okay, maybe I'll write it with here, 2. Okay, so that's the third root of x plus 1 over 6 times the sixth root of x to the power of 5. Okay, so you don't really need it if you don't want to write it like that. You can just leave it like that, and that's okay. Great. Now let's talk about the second rule. Second rule says that if you have a constant times a function, so a is a constant, and you want to compute the derivative of that, so you can take out a and then compute the derivative of x. For example, any of those rules we need to prove in general mathematics, but we are not going to prove them, we are going to use them, okay? So, for example, if you're asked to compute the derivative of 2 times x to the power of 5, what you could say here is 2 times the derivative of x to the power of 5. So we took out 2. So it's 2 times 5 times x to the power of 5 minus 1, 4. So it's 10 times x to the power of 4. Okay? Great. Now, let's present another rule. So, what about the product? Okay, so if you take f of x times g of x, and you want to compute the derivative of that, unfortunately, that's not the derivative of f times the derivative of g. The formula is different here. It's the derivative of f times g as it is, plus f as it is, times the derivative of g. Okay, so let's see different examples. Okay, so for example, suppose that you want to compute the derivative of x to the power of 5 times e to the power of x. So here we have two functions. So the first one is x to the power of 5, and the second one is e to the power of x. So according to the formula, what we need to do is take the first one and compute the derivative times the other one as it is. Plus, we take the first function times the second one. We take the derivative of the second one. What do we get here? We get 5 times x to the power of 4 times e to the power of x plus x to the power of 5. What is the derivative of e to the power of x? That's exactly e to the power of x. Okay, let me do one more. So for example, that's one. Let's do one more. So for example, let's compute the derivative of 2x squared times the square root of x. Okay. Now there are two ways to compute that. I'll show you the two ways. The first way is, okay, first of all, we can take out 2. Okay, 2 doesn't affect here. Okay, so it's 2 times the derivative of x squared times the square root of x. Now that equals 2. So according to the formula, we need to compute the derivative of the first one times the second one without the derivative, plus the first function without the derivative times the derivative of the second function. Okay, so it's 2 times. So the derivative of x squared, that's 2 times x times the square root of x plus x squared. Now the derivative of the square root of x, that's 1 over 2 square root of x. And that's all. Now you can just expand the brackets here and try to arrange that, but in the end, that gives you the derivative of that. Another way, okay, second way, so is to say that 2x squared times the square root of x, that's exactly 2 times x squared times x to the power 1/2. Now you can take out 2. So it's 2 times the derivative of x squared. Now please remember that x to the power of a times x to the power of b, that's x to the power of a plus b. So that's going to be 2 times x to the power of 2.5, 2.5. And we need to compute the derivative of that. And that's exactly 2 times 2.5 times x to the power of 2.5 minus 1, meaning 1.5. Okay, meaning it's 5 times x to the power of 1.5. Okay, so those are two different ways, okay, to compute the derivative of that. Okay, one way is to use what we call the product rule, and the other way is to use some algebra before computing the derivative. Okay, next rule. Suppose now that we want to compute the derivative of f of x over g of x. That equals 0, so gx, all of that squared. And then we take f, the derivative of f times g of x minus f of x times the derivative of g. Okay, so basically that's a formula of how we compute the derivative of fractions. Now let's do one more example. Maybe two. Okay, suppose that you want to compute the derivative of e to the power of x over x. So what you need to do, so here you're going to write in the denominator, you're going to write x squared, because that's g, and then compute the derivative of x, of e of x, e to the power of x, times x as it is, minus, you're going to take e to the power of x times the derivative of x. So from here you're going to get that it's e to the power of x, because the derivative of e to the power of x, that's e to the power of x times x, minus, what is the derivative of x? That's exactly 1. Okay, so minus e to the power of x times 1, so e to the power of x over x squared. Now if you want, you can take as a common factor e to the power of x and write it like that. Okay. Okay, let's do one more. Suppose that you want to compute the derivative of the square root of x over x squared. Okay, so again, that's x squared squared. Now you take the derivative of the first one times x squared, g of x, minus f of x at the square root of x times the derivative of x. Now that equals 2. So x squared squared, so it's x to the power of 4. Here, the derivative of the square root, that's 1 over 2 times the square root of x times x squared. And here, the derivative of x squared, that's 2x. That's 2x. So what do we get here? Minus the square root of x times 2x. Okay, that's one way. Another way, and even a better, that's a better one, is to use the algebra. Okay, so the square root of x over x squared, that's exactly x to the power of 1/2 over x to the power of 2. And that's exactly x to the power of 1/2 minus 2, taking the derivative of that. And that's x to the power of minus 1.5. Okay, and we want to compute the derivative of that, and that's minus 1.5 times x to the power of minus 1.5 minus 1 minus 2.5. Okay, so if you, by the way, if you just do the algebra here in the end, you need to get exactly the same, of course. Okay, so two different ways to get exactly the same solution. Okay, now let's continue with one more rule. Now let's talk about how to compute the derivative of a composite function. So the formula says that if you have a function f of g of x, so that's the composite function, and you want to compute the derivative of that, what you need to do is to take the derivative of f and plug into it g times g tag x. Okay, so let's see how we use that. We'll do a few examples here. For example, let's see, so suppose that you want to compute the derivative of 2x to the power of 2. So that's a composite function. Why? Because if you think about it, what we did here is to take something squared when we plug into it 2x. Okay, so that's a composite function. So according to that, what we need to do is to compute the derivative of f. In this case, we have f, that's exactly the bracket squared. Okay, because in the end, think about it, we took something squared and we plug into it 2x. Okay, that's what makes it a composite function. Okay, so in this case, how exactly we compute the derivative of something squared? It's 2 times the brackets to the power of 1. Now, here we need to compute the derivative of f and then plug g of x. G of x, it's 2x. So 2x. And then times the derivative of gx, so the derivative of 2x. So it's going to be 4x times the derivative of 2x, meaning 2. So a times x. Let's do some more examples. What about e to the power of x squared? So let's compute the derivative of that. So if you think about it, what we did is we took the function e to the power of x, and then we plug into it x squared. Okay, and that's what makes it e to the power of x squared. So in this case, who is f? F is e to the power of x. And who is g? G is x squared. So let's compute the derivative of that. So we need to take f, the derivative of f. The derivative of f, that's the derivative of e to the power of x, or the derivative of e to the power of x, that's exactly e to the power of x. But then we need to plug into it g of x. So that's going to be e to the power of x squared times the derivative of g of x, meaning the derivative of x squared. So that's exactly 2 times x. Okay, so let's write e to the power of x squared times 2 times x. Okay, many times you write before 2x and then the exponent. Okay, so but you can leave it as it is if you want to. Okay, now let's do a few more. So for example, let's compute the derivative of e to the power of 2x squared plus 1. Okay, so again, here we have e of x, and we plug into it 2x squared plus 1. So we are going to compute the derivative of e of x, and that's exactly e of x. We are going to plug the function g of x into it. So 2x squared plus 1 times the derivative of g of x. That's exactly 1. What is the derivative of 2x squared plus 1? So that's e to the power of 2x squared plus 1 times, what is the derivative of 2x squared? So it's 2 times 2x, and the derivative of 1, that's a constant, and therefore 0, so plus 0. So in the end, we get that that's e to the power of 2x squared plus 1 times 4x. Okay, let's do one more on the next page. Suppose that you want to compute the derivative of the square root of 2x squared plus e to the power of x. Okay, so how exactly we're going to do that? So if you think about it, so what we did is to take the function that is the square root, and then we plug into it 2x squared plus e to the power of x. So that's f, and we plug into it g. So according to the formula, what we need to do is to take the derivative of f, so that's 1 over 2 square root, and then plug into it g. So 2x squared plus e to the power of x times the derivative of g. So 2x squared plus e to the power of x. Derivative of that. And the derivative of that, that's exactly 4x plus e to the power of x. Okay, so basically we covered all the different rules of derivative. On the next slide, I'd like to show you two more examples regarding the derivatives in general. Okay, so before we continue with the two examples, I want to mention a remark here. When we talk about continuous functions, we said that the exponential functions, the linear functions, the quadratic functions, and the absolute value were all continuous. Now here, I can also tell you not exactly the same, but you need to remember that all linear functions, quadratic functions, exponential functions, okay, and in general polynomials. Please remember that polynomials. When I say polynomials, polynomials are linear functions, quadratic function belongs to the polynomials, so it's part of the polynomials functions. Okay, so all of those functions are differentiable at any point. When I say differentiable, I mean you can compute the derivative at any point of those functions. Okay. Now, if you want to include here also the square root, okay, it's not at any point that are part of the domain. Okay, because when it's the square root, it's not defined if it's a negative value, if the input is a negative value. So again, if you look at all the linear functions, the quadratic function, exponential function, polynomials in general, okay, and even the square root functions, okay, they are all differentiable at any point that are part of the domain. Okay, now that we know that, let's start with the first example. Suppose that you're asked to compute the derivative of f of x that equals to x when x is less than 0, and x plus 1 when x is between 0 to 2, and x squared minus 1 when x is bigger than 2. Okay, now how exactly we are going to do that? So first we can say that the derivative of f, when x is less than 0, we know that f returns x, and the derivative of f in this case is 1. If it's somewhere between 0 to 2, so the derivative of x plus 1 is 1, because the derivative of x is 1, the derivative of 1 is 0. And if x is bigger than 2, then the derivative is 2x, because the derivative of x squared is 2x minus 1, the derivative of minus 1 is 0, so 2x. Okay, now the question is, what happens at 0 and at 2? So now you need to check it apart from this. Why? Because the function at 0, okay, if you look at the right side of 0 and the left side of 0, the function is different, because on the left side of 0, the function returns x, but on the right side of 0, the function returns x plus 1. Now you need to remember that the derivative is defined by limits. That means that we need to check what happens on the right limit and on the left side limit. Okay, so what happens when we approach 0 from the left and 0 from the right. Okay, so we are going to ask the same question for 2, but let's start with 0. So suppose now that you want to compute, we want to find the derivative of f at x equals to 0, of course, if it exists. Okay, maybe it doesn't exist. Okay, so what we are going to do, we need to compute the limit of f of x minus f of 0 over x minus 0. So that's the definition, the second one, when x approaches 0. So that's the limit of f of x. So now we're going to split it into two. Okay, so we're going to ask what is the limit when x approaches from the right, and what is the limit when x approaches from the left. Now, if we get the same limit, that means that the original limit exists, because that's how we define the limit. Okay, so we're going to check those two decided limits. So let's start by the first one, the limit when x approaches 0 plus of f of x. So when I approach x from the right, so from the right here we have a function returns x plus 1 minus f of 0. F of 0, that's 0 plus 1, so minus 1 over x minus 0, so x. So here we have x over x, and that means that we get 1. Okay, let's do the same, but now when we approach 0 from the left. So what do we have here? So f of x, again, now we approach from the left. So it's x minus f of 0. So it's 1. And over x. Now, when x approaches 0, what do we get here? We get that that's infinity. Okay, and that means that those two are not equals. That means that the limit at 0 doesn't exist. So we checked what happens at 0, now we need to check what happens at 2. Let's do it on the next slide. Okay, so now we need to understand if the derivative at 2 exists. So let's check what happens with x equals to 2, the derivative at the point x equals to 2. So again, we use the same definition. So limit when x approaches 2 of f of x minus f of 2 over x minus 2. So again, we're going to split it into two limits. The limit when we approach 2 from the right, and the limit when we approach 2 from the left. If we get the same limit, then the conclusion is that the original limit exists. Okay, so when we approach the function from the right of 2, we get that it's x squared minus 1. So the right to x squared minus 1, and we need to subtract f of 2. F of 2, that's 2 is 0, so f of 2 is 3, so minus 3. Over x minus 2, so what do we get here? That's the limit when x approaches 2 from the right, so x squared minus 4 over x minus 2, and that's classic, so x approaches 2 from the right, x minus 2, x plus 2, over x minus 2, those two cancel, and then we get 4. Now, let's see what happens when we approach 2 from the left. So if we approach 2 from the left, somewhere close to 2, so the function returns x plus 1. So here we have x plus 1 minus f of 2. So f of 2, again, 2 is here. So we like 2 here, we get 3, so minus 3 over x minus 2. So that's the limit when x approaches 2 from the left of x minus 2 over x minus 2. And that's exactly 1. So 1 doesn't equal to 0. And therefore, the derivative at x equals to 2 doesn't exist. Okay, so in the end, we can say that the derivative of f, what is the conclusion? So the conclusion is that the derivative of f of x is if x is bigger than 2, then it returns to x. And here we see that if x is between 0 to 2, and also if x is less than 0, then it returns 1. So we can say that if x is less than 2 and isn't 0, because we know that at 0 the derivative doesn't exist, then it returns 1. Okay? If you want, you can leave it as here, okay? But if you want to write it in a short way, okay, so you can write it like that. Okay. So great. Now let's continue to the second example. Example number 2. Now, let's prove, we want to prove that the derivative of f of x that equals to the absolute value of x isn't differentiable at x equals to 0. Okay? So again, what it means isn't differentiable, so it means that the derivative at x equals to 0 doesn't exist. Okay. Now let's prove that. So basically, we are going to use again the definition. So we want to show that the limit when x approaches 0 of f of x minus f of 0 over x minus 0, this limit doesn't exist. So in order to do so, we are going to split it into 2 limits. We are going to see what happens when x approaches 0 from the right and from the left. Now, here, let's start with x approaching 0 from the right. So f of x, that's the absolute value of x, minus f of 0. So the absolute value of 0, that's 0, right, over x minus 0. So that's the limit of the absolute value of x over x when x approaches 0 from the right. Now, I hope that you remember that the absolute value looks something like that. Okay? Now, when I'm approaching the absolute value, the function, from the right side of 0, the function returns exactly x. So here we're going to get the limit when x approaches 0 plus of x over x, and therefore the limit is 1. Okay, please remember that the definition of the absolute value of x, that's x in case that x is non-negative, and minus x in case that x is negative. Okay, so when x is somewhere close to 0 from the right side, it returns x. Okay, that's what I did here. Now let's see what happens in case that we compute the limit when x approaches 0 from the left. So what do we get here? So the absolute value of x minus 0 over x minus 0. But now when I'm approaching x from the left, the absolute value returns minus x. So here we get minus x over x, and that's exactly minus 1. And here we can see that the limit isn't the same. Therefore, this limit doesn't exist. And if it doesn't exist, that means that f is not differentiable at x equals to 0. Now, one more thing here that we can understand from this example is that when we have corners in functions, so that's a corner, the function is not differentiable at those points. Okay? So for example, if I ask you, suppose that you have a function, something like that, and then you have a corner here, so you can say automatically that on this point here, the function is not differentiable. Okay? So that ends lecture number 8. Now we'll continue to lecture number 9, and we'll see different applications of derivatives. See you on the next lecture.